Okay, so let's officially start. Hello, everyone. Welcome to episode 65 of Warsaw Quantum Computing Group Meetups. My name is Pavel, and I will be the host today. And today we have pleasure to host a talk given by our great speaker, Linden, from Jagiellonian University in Krakow, and she will tell us about Google's Willow quantum chip, pioneering advancements in quantum error correction and scalable computing. So this is the title of the talk. Before we start, just a few announcements. So as you can see, this meeting is recorded, so later we'll upload the recording to our YouTube channel, hopefully. And if you have any questions, we've agreed with Alex that there will be some breaks during different parts of her talk. So you can either post your questions on the chat and we'll try to ask them during the breaks, or during the breaks, you'll be allowed to raise your hand and ask a question. Okay, before we start, I would like to thank our strategic partner for supporting us, Sonovero R&D, Onyx, Quantum.io, Cogit, and ThinkQubit. And we'd like to thank our honorary partners for helping us advertising these events. Okay, that's all from my side. And Alex, if you are ready, you can start sharing your slides and the Zoom is yours. So first of all, thanks for accepting our invitation.
Of course,
It's,
thank you for inviting me.
it's great to have you with us again. And yeah, we can start.
Is my screen visible?
Yes, I can see it.
Okay, great. I will be talking about Google's Willow quantum chip. If anyone here is trying to keep up with the news in the quantum world, they probably heard about it. It was quite widely advertised and also not only in scientific circles, but also in pop science media. And the goal of this talk is to see what Google claims about Willow and what information is publicly available to us. And then I will try to explain all the different building blocks that go into this processor. One thing that is, of course, unfortunate is that we do not have specific information on how it was implemented, like how the algorithms or the different methods of error correction were implemented so that they achieved the results that good. But we can understand at least that the methods they used can be very much viable. All right. And in terms of the level, first of all, like everyone should be able to understand things even if they have never done anything in quantum error correction. I will do the introduction from the beginning. And because I will cover a range of topics, I think that unfortunately I am not able to go into too much detail, but I hope that even for people that do deal with quantum error correction in their work, there will be something that will be interesting. So the general structure of this presentation will first we'll look at general Google's claims about Willow, where they come from. Then I'll provide a short introduction to quantum error correction. Next, we'll see Willow's performance and what data we have, and also what Google says about the data. And finally, the summary. So Willow is the chip that was introduced by Google Quantum AI on 9th December, and it was introduced by posting two things. First was a blog post on their Google Quantum AI blog. And this post served as, let's say, quote unquote, advertising, which then was shared by the media. and some of its claims aren't specifically scientific, but more marketable. And then there was the Nature article, or an article that was published in the journal Nature on the same day. This is the picture, of course, represents what the chip looks like. Now, the claims here are mostly from the blog post and from what Google has said in interviews and other things, not only meant for the scientific community. And after this talk, because here I'm not explaining what everything is, I will explain it during my talk. And then afterwards, we can revisit it and maybe discuss it in some more detail. So first of all, a very big accomplishment of Google is that the processor operates below the threshold. And the threshold is something I'll define later, but essentially what it means is that when we use more qubits in our quantum computer, we have the fewer errors we have, which is a very big achievement because usually errors reproduce exponentially. The more qubits we have, the more errors we have, to the point that very quickly it becomes completely unmanageable. Second of all, it constitutes one of the first compelling examples of real-time error correction, quantum error correction, on a superconducting quantum system. And that essentially means that we're not doing we're doing calculations, and during these calculations, we are also correcting errors while the calculation is running. The reason why it's hard to do that is that quantum computations, as you probably know, can be very, very fast. And we need to catch up with error correction, which in this case is also done on classical machines. Next, the achievement it's called a beyond break-even demonstration, and that means that the arrays of qubits have longer lifetimes than the individual physical qubits do. We'll see that to employ quantum error correction, almost always we use more qubits and a sort of redundancy. So we use more qubits than absolutely necessary for the computation. And that means that this cluster of qubits has a longer lifetime, so it's usable for longer than individual qubits. And next, this is a claim that was, I think, the most visible in different articles that I read, and that Willow performed a sort of a computation, and it was in under 5 minutes, and it would take today's fastest supercomputers 10 to the 25 or 10 septillion years, and of course, like this is the longer time than the life of the known universe. We'll look at this claim a couple of times, I think. Now, the reason why this talk will focus mostly on error correction is that Willow is mostly an accomplishment in quantum error correction. They have their processor Sycamore, with which they achieved, or they claimed, quantum supremacy in the year 2019. And that's already a big accomplishment. So the difference between those two mostly lies in the quantum error correction. And I want to explain how it works. So first, that was a short introduction. I will pause probably after the quantum error correction part introduction. Quantum error correction is created and was created because quantum computers are very prone to noise. And noise pretty much can destroy our computation because it will make it less reliable. It can make our qubits completely unviable. And the more qubits we have, the more, as I said previously, like the more errors we'll usually have. And this is one of the biggest bottlenecks in creating scalable quantum computing. So to overcome this is a very big milestone. Now, we want to correct the errors. I will explain what kind of errors we can have. But first, error correction in general. Of course, quantum error correction lays in some ways on classical error correction, which is a very developed field in information theory. And I will always say here, almost always, because I do not know all the different types. There's a lot of types of quantum error correction, but let's say almost always is used with redundancy. So we have our information, we introduce more information that helps us to encode the solution that can then correct the errors. And then to be exact with my language, the phases of error correction. So what we do actually is first, before the computation, we encode, in this case, our qubits somehow. So we introduce the redundancy in a specific structured way. Next, we detect error. So this is where the computation starts. And then we have to have machinery to detect those errors. And when we detect them, again, we have to have machinery to be able to correct them. Sometimes we are able to tell there was an error, but we don't know how to correct it. And then finally, we decode it. So we remove this redundancy and we're left with information that hopefully does not have any errors or has fewer of them. So there's many moving parts here and they all need to work. And now to introduce a bit of classical error correction, I will show a quantum error correction example next, which is based on this example. Is one of the most basic codes, the repetition code. And the codes are basically the systems of the different phases that I talked about a moment ago. This situation is the following. We want to send a single bit, so 0 or 1, through a communications channel that is noisy. Noisy means there are some kinds of errors. So in this case, we only have 0 and 1, and the only type of error we can have here in this specific example is 0 flips to 1 or 1 flips to 0. For whatever reason, that's because of noise, and we don't know its structure, but we don't need to. Now we want to encode it, so we want to introduce the redundancy. Now, some terminology. First of all, we have our bit. And this will be called the physical bit. And then we introduce 2 more bits, kind of ancilla bits, that are the same as the physical one. So for example, for 0, we introduce 2 more bits that are set to 0. And this array of 3 zeros now is called a logical 0. Similarly with 1 will become a logical 1. Then we send our message that is now encoded through a channel, through the channel that we have, and we will get a 3-bit message. Now, to detect the error, what can we do? So we'll notice either 000, 111, or something else. And if we see the something else, then we know that an error has occurred. We don't know yet which one, but this is the part of detection. We know that there was an error. Now, together, correction and decoding, we employ something that's called majority voting. And that means that we count the values. So how many zeros there are and how many ones there are. And then the value that appears more, it will be our message. So for example, if we have 000, it's only a 0, so we shorten it to 0 and that's our answer. But in the situation that we have 010, we have 2 zeros and 1, 1. So we'll be left with a 0. And finally, if we have 0, 1, 1, we have one more 1. Okay, we have 2 1s and 1 0. That means that we'll be left with 1. Now what you can immediately notice here is that we can correct 0 or 1 error. Because if there are 2 errors, like in the last example, we get 1, even though we wanted to have 0. So we can ask, what can we do in this instance? Well, we can introduce more redundancy. That would be the obvious answers. So instead of a 3-bit repetition code, we can have 5-bit repetition code. But then we can have, for example, let's say 4 errors. And what then? So we can introduce redundancy forever. However, we don't have infinite resources. So we want to employ some tricks to be able to keep resources to the minimum while still correcting as many errors as we can. We'll talk now about the 3-qubit bit flip code. So this is an analog of the 3-bit bit flip code. So quantum error correction is a little bit different than classical error correction. That's because of simply laws of quantum mechanics. So we have multiple obstacles that are in our way to create a good code that will correct our errors. First of all, there is the no cloning theorem. The no cloning theorem essentially means we cannot clone a qubit in a state. That's also connected to the last obstacle here. But that's the first rule. We cannot clone the state of our qubit. Second of all, as we know, the number of possible states of a qubit is a continuum. There's an infinite number of states we can have, simply because we have alpha and beta in the general representation of a qubit that can be complex numbers, and that already introduces an infinite amount. So similarly, we can have an infinite number of different errors that can appear on a single qubit. Fortunately for us, there are some classes that are much, much more common than others. And finally, measurement destroys quantum information. So that means we cannot essentially peek under the hood to see what the state is at a given moment to help with our corrections. What is sometimes done, and what is done in the case of Willow, is we assume that errors manifest as gates. So we can imagine the noise randomly sometimes adds a gate to our circuit. And here, the bit flip channel specifically, we only want to consider one gate, which is the X or the NOT gate, or the poly sigma X operator. And in the bit flip channel, the qubit might be flipped with some probability P. And that means that if we have a state psi, it will be changed to the state X psi. That's what we know. So this is a very simplified model. But nevertheless, in the real world of quantum computation, it definitely can help us correct some errors. So now, we had physical bits and logical bits. Now we have physical qubits and logical qubits. The general representation of the qubit, of the state of the qubit, will be A of the base state 0 plus B of the base state 1. We employ similar tactic to the 3-bit flip code. And we essentially introduced 2 more qubits with also the state in the same state. So we'll have A in now this base state 0, 0, 0, and B in the base state 1, 1, 1. And this is our logical qubit. The way we do it is represented in the circuit. We do it with C-notes, and the logical qubit is here represented on the right side as the ket of psi L. And now we have, this was only our encoding so far. And now we pass our 3 qubits through the bit flip channel. So this is where the errors occur. Now, what we did here is only the first part of the circuit. The noisy channel part is that what also we did. So now we are at state psi 1, the state which might have some errors. If you look at the table above, the bit flip column means on which bit the error has occurred. The second column is the possibilities for our state psi. And then we have M1 and M2. They are called syndrome measurements. A very important thing in quantum error correction, in which we measure something that is not the actual state that we want to correct. So in this case, if you look at back at the circuit, if you look back at the circuit, we're introducing 2 more qubits in state 0 and using CNUTs on our state, and then on one of the also the redundant qubits. And then we measure them. So this is how we overcome the roadblock that is no measurement of the state, because we'll destroy it before the end of the computation or before the correction. And we measure this. So we're not actually measuring the state. We're measuring some information about the state, which in this case is an information about the error that occurred. So M1 and M2 are the results of the 2 measurements that we did. In the recovery, we'll say how we can fix what we have, and then Psi2 will be the final corrected state. So let's look at the first row. If we had no errors, we'll have our state that we had previously. Both syndrome measurements will be 0. And for that, in each case, we'll apply 3 gates. But in this case, it will be 3 times identity. We don't have to change the state at all. Next, if the error occurred on bit 1, we can see that both near A and B, obviously, the bit was flipped. So you have A 1, 0, 0, 0 and B 0, 1, 1. And in this case, we'll have a 1 on the second syndrome measurement. Now, what that means is if we have this state, that simply means we need to introduce an X gate on this first qubit. That's because the X gate is reversible. If we apply X gate 2 times, we get the initial state. And that's exactly what happens. It works similarly in the case of 2 and 3. It is important to note, though, that during error correction, of course, we don't see the whole table, or we don't see the Psi1. We only see M1 and M2. And this is what we use to deduct our state. All right. This is the general outline where you can see, first of all, the syndrome measurements is something to note. What we actually see, we don't see the state. We see some additional information that we gained about the error, not the state. And we need to know how to be able to recover our state. So the detection part is the syndrome measurements. And now the correction part is recovery. And here it's fairly easy. Similarly, if we want to be able to correct more than one error, we'll have to introduce more qubits, which are more valuable than gold. So we don't want to do that usually. So it works very similarly. Now, actually, let's look at what Willow uses. Willow uses something that's called a surface code. It's very popular. It's one of the most popular codes right now in the error correction world. It is quite complicated to explain everything formally, which is why I won't do that, but I will provide an intuition to how they function. Their surface codes are codes that are usually defined on a 2D array of qubits. They are also a subclass of so-called topological codes. And why topological? Here it says usually defined on 2D array of qubits, but what is interesting about them is imagine we can bend the surface code in any way. Imagine we can make a tube out of the surface code. So it is as if we took the rightmost and leftmost qubits and we joined them together. Moreover, we can also join the top and the bottom, and that will create a torus, so a donut-like structure. And this is also done. You can also have a surface code that extends into infinity, although this is not really possible to implement, of course. But we'll stay with the easy example that is used the most. So we just have some array of qubits. Here the qubits are the circles, where some of which are white and some of which are red in the picture. And then also they belong to two classes of codes. So we have a general classification of codes. They're topological codes and also stabilizer codes. Stabilizer codes can be thought of intuitively as we can detect sort of the topology or the shape that the errors take, and we can create structures that will stabilize it. So we'll add more or change something so that the errors that are present are nullified. And stabilizer formalism is a big field in itself, so it will be hard to explain here. But let's look at the picture. So as I explained, the circles are the qubits. And the vast majority of errors that we'll encounter in current quantum computing devices are X errors or Z errors. Of course, Pauli errors. And so this surface code at least accounts for those two types. And the white faces that have the letter Z in them, you can think of them as the syndrome measurements that we had before. So we'll be able to measure them, and just as with the Z that are more pink or X that are more, let's say, red, we'll see that something is wrong. Now I want to play a little game or a little puzzle. But first I need to introduce the rules. Let's look at the error with the Z's. If we have an error there, the syndrome measurements of the specific error, so in this case the Z error, will light up, but only the ones that are neighboring to the qubit. This is why only two light up. Second rule is that because the gates are reversible, you can look at the axis now. If near a syndrome measurement, around a syndrome measurement, we have an even amount of errors, this syndrome measurement will not light up. So this is why the X that is between the two dots to the left is not lit up, but the ones above the upper qubit and below the bottom qubit are lit up. The half circles here are the same as the squares. They have the same function. So this is the rules. But of course, when we perform the computation, we'll only see the syndrome measurements, as I mentioned. So I will give a little bit of time now to look at this puzzle and tell me, you can tell me where the errors occurred. So you can we have these two Z measurements, syndrome measurements, and the two X ones. This is what we will see during quantum error correction. And now we need to infer. So we detected some errors, but to be able to correct them, we need to be able to tell or guess where the errors occurred. Okay, we can see the answer now. All right, there has been an answer that 3, 2, between two Z's. See, this is a good possibility, and this is possible that would happen and more likely. But here, this was a tricky answer, because a tricky question. Because look, we had these three errors. If I looked at it correctly, I think that I have the Z that is to the left of the two qubits is white because it has an even amount of qubits near them. Same with the upper Z. They are white because they have an even amount of qubits that have errors on them that are neighboring. And so the two errors that are lit up are from the rightmost and bottommost qubits in the array of three qubits that constitute the error here. So this is already, I wanted to show how the simplest solution is not always correct in the case of errors, although of course it is less likely. And in the second case, we can see a different array of errors, which in this case is three errors that are, let's say, on top of each other. And this is the situation where you only have one X light up. Excuse me. You have only one X light up. Then you immediately think, you should immediately think there is some other error near it, because otherwise there would usually be two syndrome measurements lit up, just like in the case of the Z, although in this case this was not correct. You can look at it now and verify that this is how the syndrome measurements will look based on these errors. Yes, the semicircles can represent the folding, although in this case, it's not necessarily folded, but you can fold it with the semicircles. For now, you can, for the purposes of this talk, you can just think of it as another square. And now is a good a moment to stop because this is the end of the introduction to quantum error correction. And are there any questions? You can write on chat, or you can also ask it by unmuting yourself. There is a question. Let me read it. This is a good question. I will read it out loud for the recording. So the question is, for the 3-bit representation case earlier, for the occurrence of just one error, that is a bit flip, already 2 more qubits had to be employed to not tamper with the decoherence issue. And does this pattern continue exponentially? Well, during first attempts at quantum error correction, this was the case. So we just need to add more and more qubits to be able to correct more errors. So for example, say we have 5 qubits. Then we can correct to up to 2 errors. Because if we get 3 errors, you can see the majority will be wrong. But now with the more advanced structures like surface codes, it's not that bad. However, there are more, it's not a very simple answer, and I definitely don't have the exact number or like the way it scales up now. But if we have more qubits in an array like this, so in a topological code, these qubits are connected. So each qubit has exactly 4 neighboring qubits, as you can see on the array here. And the biggest the surface code, or how we can say the biggest the surface code distance is, the more connections we have. And during the computation, like naturally, because of the way quantum computers are built, some of these connections are weaker. Some will be stronger, some will be weaker. And the bigger the surface code, an additional problem is the weakening of these links between qubits. And this is just one of the issues that comes with scaling up. So every single logical qubit that we make is extremely resource intensive. So in this case, you can see already how many qubits we're using. And so because we're using qubits for the syndrome measurements, not only the logical qubits that are the circles. I hope that answered your question. Yeah, the general answer is just, it is very bad. I will not tell you the exact way of scaling up because that depends on the code that we have, but it's completely not viable with the devices that we have now. To scale it up to a level where the computation is practical in any sense. This is why advancements like these are very necessary. All right, if there are no more questions, then I can, oh, there is it, okay. One more topic from quantum error correction is the threshold. The threshold, it's not best to define it, so to say, but to see what it is through the theorem. So there's an important theorem in quantum error correction that's called the threshold theorem. And here in the general sense, it's not very formal, but it is correct. The theorem essentially says that if we have an error per physical gate or time step, so the error, of course, like per one gate that we apply, how many errors do we get? Or per a sort of time state that we designate. How many errors do we have? If it stays below a certain constant threshold that always exists, then increasing the code size, so increasing the size of here, in our case, the surface code, will decrease the logical error rate. So the question that we had was very good in that sense. I hopefully at least illustrated that it is very hard to scale up. So in this case, we can scale up and not have the consequences. To the contrary, the more qubits we have, the fewer errors we get. The way it's usually, we usually find the error rate, to be honest, is we graph it. We graph the errors, and then we look for the point of crossing. So there will be the crossing where the bottommost line, in this case for a certain distance, will be below, and then it will be above, and vice versa. The one that was above will be below. And that point of crossing is the threshold. So as you can imagine, depending on on our code, it can move, but it always exists. So now what it means to stay below the threshold, that might be nigh unthinkable to people in the very distant past of last year. Because very quickly we move beyond this threshold. For our devices, we overshoot it very, very quickly. When I was doing experiments for my paper that I co-authored, very quickly, even with the smaller surface code that we have here, we already went beyond this threshold. So it's very early. So to stay below it, that means here to the left of the threshold, is big in itself, but it allows us to do really incredible things with error correction. So here the d is the distance. You can just think of it as the size of the surface code that we have. So adding more qubits usually means more trouble. In this case, it means less trouble. Now, to the right is the spec sheet that's also available online if you cannot see it very well, because it's very small. And I'm not qualified to speak about every single value that is here. But what I find to be important here is, first of all, the very general idea of qubits. It has 105 qubits. Because we can have a varying range of errors depending on the noise channel. We can have different connectivity between the qubits. We can have a different quantum error correcting code. We can have a qubit that is itself implemented differently. The number of qubits in general in quantum computers doesn't mean as much. Of course, it's better to have theoretically 50 qubits to perform the operations on than one. But sometimes the one can actually perform these computations, and the one with 50 qubits cannot do anything. But it's important information, especially knowing that here going up means something, because that means we'll have less errors. Then we have improved operational fidelities and mean coherence time. Essentially, it's important here that we have a comparison to Google Sycamore, which I already mentioned. And it is a big step from Sycamore in such a short amount of time. Now, for the decoding part of quantum error correction, we have two decoders. and one is a neural network-based decoder. So I think you can already see how the puzzle that I presented with surface code, it would be very tempting to introduce neural networks to it. This is the sort of thing that they can excel at. And one that is, we call it a harmonized ensemble of correlated minimum weight perfect matching decoders. The second class is the one that I'll introduce in a moment. And finally, the surface code that we have has this size 7, and it has 49 data qubits. So the ones that actually hold our data. Then 48 qubits that are used for measurement, and then 4 additional leakage removal qubits. We also have another issue in our quantum error correction or in quantum computers in general. This is leakage. You can think of it as an out of range error because that essentially means that we're going out of the Hilbert space that we have with the state of our qubits, with how our qubits behave. This can be catastrophic for computations, and so it's important to introduce some redundancy to combat that. Of course, on the bottom of the spec sheet, we also have the 5 minutes versus 10 septillion years. We have circuit repetitions and the rate of error. I'll skip this for now, but this information is available online if someone wants to go deeper into it. So Willow itself has a layout that is presented on the left. So each of the circles is a qubit here, and we can see the connections between them with the blue lines. Now, it says most, but not all errors have been detected. That is to be expected since we have a myriad amount of different types of errors. But the fact that most have been detected is already a good sign. Now, they said that this information from now on and is from their article and the scientific article and not the blog post. So this is more, let's say, grounded. So the leakage that I described but above a bit ago, and then the stray interactions. So stray interactions, directions that we don't want to happen, they might become a dominant contributor. So they're already saying for the future, when we'll be increasing the number of qubits and we expect errors to go down, these ones might prove to be the most difficult one to combat, and this is the one that they will target in the future. Next, the larger codes are less sensitive to component level fluctuations, which again is a plus since we're operating below threshold, we want to have the larger code. And next, it says that broke through essentially in Sycamore, there were these high energy impact events where the sort of energy of the system jumped up very suddenly and introduced a sort of floor that they couldn't get through before. And it was 10 to the minus 6. So it is very low, but still it's not enough to have viable practical quantum computation. So if we stated that with that floor, it wouldn't be good. Still, it would be an achievement, but not as significant. So what Google did is not only develop this chip, but the development of it is interesting in that they did not necessarily have just one idea that was revolutionary. They're using the fairly well-known aspects of quantum error correction and the components of surface code, of, we'll see, the benchmark that they use, the algorithms that they use for decoding. They are very well known and they are used. So they're essentially doing micromanagement to be able to fine-tune it enough where we go step by step in the direction that we want to go to, which is, of course, viable quantum computing on a larger scale. Now, we can look at the real-time decoding that they have. And of course, first is the neural network. I will leave that one. But then the second one is minimum weight perfect matching. It's one of the most popular algorithms for decoding. It's a classical algorithm. And so the way it works, they have a separate machine that is getting information about syndrome measurements in real time as the computation proceeds. And it has to decode the errors and send it back to our quantum computer so that we know how to correct them. So this is also quite hard to achieve, I believe, to have a classical machine that can keep up with the quantum one, with the decoding. And now, so the algorithm is called minimum weight perfect matching, and is what we want to find is exactly that. So we want to find the minimum weight perfect matching. It lies within the field of graph theory. So essentially, we have our vertices, we have our edges. And now I can explain what that is actually. So first of all, a matching in a graph is just any set of edges that don't have common vertices. There's the fairly small example on the bottom. We can see that, for example, AF, BC, so AF and then edge BC, they are a matching, but something like FB, BC is not a matching. Next, a perfect matching is a matching that will include every single vertex of the graph. So we need to cover all the vertices that we have. And then a minimum weight perfect matching may be self-explanatory, but this is what works in a weighted graph. So each of our edges has a certain weight associated to it. And we want to find a matching with the smallest total weight. Here you can see an example of a graph with a minimum weight perfect matching. And this is a simple graph, very, very simple, very small graph. And the numbers that I chose are ones that will make sure that this perfect matching is correct, and hopefully it is. But so this is definitely a perfect matching. You can see all the vertices are covered. However, if we analyze it further, we can kind of see the challenges that will be presented to the classical computer that has to find such a minimum weight perfect matching. For example, let's say we have an algorithm that looks for the smallest weights first, and we notice the edge BF. So if we want to build a greedy algorithm, this is the edge that we'll choose first. But we need to see that if we choose that edge, there's no way to connect A, because then we'll break the matching. It will not be a matching anymore. So that's the first thing we can see. Second of all, if we choose one edge, if you choose one edge, then you need to consider a lot of other possibilities. Let's say we choose BE. Well, then it seems like it's the same weight as AB, and there can be a perfect matching made using the edge BE. But we have to notice that if we choose this edge, then we need to choose AF, which has a very large weight comparatively. I will not go into the specifics of the classical algorithm, but I will explain. So there is an algorithm that does this in a, let's say, fairly efficient manner. Efficient enough for our needs anyway. So the way we use it on surface codes. So the surface codes that I showed you are in fact called a rotated surface code. And the rotation here comes from the fact that this is the original layout of a surface code. This is how it was originally developed. Right now, the rotated version is used most commonly. But here we switch essentially qubits and syndrome measurements. So first of all, imagine we just look at one type of error. So let's say we look only at X errors. And in this case, to the left, you can see the representation of the surface code. So the vertices here will be the stabilizers, but here we can just look at the X stabilizers, for example. The stabilizers come from the fact that surface code is the stabilizer code, but they are used for detecting errors. And the qubits are the edges here. So it makes sense if you think about it, since I will go back. Let's look at X errors. Every qubit will be neighboring, well, one or two, usually two X syndrome measurements or stabilizers. And here we only look at X errors, and every single edge neighbors at most two of the stabilizers. And then the weight of each edge, how do you look at that? It is the Manhattan distance between the two stabilizers that we have. So let's look at 1 and 2. We just go from 1, 2 steps up, we get the distance 2. So on the graph there, between 1 and 2, there's 2. But let's see 1 and 3. In the Manhattan distance, also you can think of it, it's called sometimes taxi distance. And it's based on the fact that in Manhattan, the streets are made in a grid-like pattern. So if we are in a taxi, the taxi can only go essentially on the grid. So the way we calculate distance is, if we want to go in a taxi in Manhattan from 1 to 3, we go up 2 times. So we go from 1 to 2 and then from 2 to 3. And we can see the distance there, assuming the qubits there, the edges, each of them have a weight 1. Then we should have 4. And we can see on the graph that between 3 we have 4. And this is how the graph is created. And in this case also, it's very easy to find the minimum weight. Okay. So now let's say we have Willow, we have our processor, we have our quantum computer, and we want to check how efficient it is and whether it's better than our last one. And we do it in a similar way that we'll test our classical computers, classical machines, meaning we'll employ a benchmark. Now the benchmark here is something that is chosen by the group that does the benchmarking. So they will obviously choose the benchmark that is best. Now the benchmark that was used here is random circuit sampling, and this is the same benchmark that was used in proving or in stating quantum supremacy claim. The quantum supremacy claim of 2019. Now, I'm saying claim
because I'm saying claim here because, well, it was disputed. It was definitely regarded as controversial. First of all, Google claimed similarly that there was a huge difference between the time that it took to calculate the benchmark. I will explain what it is in a second. And in what actually was, and the classical one. So classical computer and quantum computer. Essentially asserting quantum supremacy means that we can prove that there is something that quantum computers can do better than classical computers. Of course, here we want the difference to be significant. And as it is usually with quantum algorithms, I have to say, is that first we invent a solution and then we invent a problem. So we think about what can quantum computers be better at than classic computers. And the answer that we have that works is that, well, quantum computers should be better at simulating quantum computers than classical computers. I think that's rational to think that. Now, in 2019, with Sycamore, there was the same benchmark was performed, and very soon later, IBM claimed, and also some other scientists, that, well, the difference isn't that large because for the data that they tested it with, there exists a classical algorithm that can do it much, much faster, making the difference not as stark. But at the same time, if we scale it up, so if we use more qubits, the classical solution drops off and it's not as good anymore. I won't say I don't have a definite answer, of course, whether that was the proof of quantum supremacy or not. There is a certain amount of belief, and it's not entirely a yes or no question whether that was proven. And here, a similar claim is made. Another interesting claim that was here made in the blog post but wasn't made in the article was that the sentence here, so the performance comparison, that it lends credence to the fact, to the interpretation of quantum mechanics of the parallel universes. So, as I understand the reasoning, is in only 5 minutes, so many calculations were made that it would make sense that the calculations were made simultaneously in multiple different universes. This claim was highly, highly disputed. And, well, my personal opinion is that it does not give us any more information about the existence of parallel universes, or, as they said, the credence to this interpretation of quantum mechanics. But it is something to take under consideration here in terms of, well, how much of the blog post is marketing and how much of it is science. So here I would recommend to look at the Nature article. Now, with the random circuit sampling, I already said that we want to simulate a quantum device, or, well, have our quantum device. And in this case, well, it is what it says. So there's a way in which we're generating random quantum gates. It's usually done on a certain level. So we apply a random 1 qubit gate, then random 2 qubit gates, random 1 qubit gate, etc. But the gates are random. And here, usually with simulations, classical computers rely on some sort of similarity, or they're very good at making so-called shortcuts when simulating quantum computers that made them be very good at it. So far, so that other than this benchmark, they've been very close to quantum computers in terms of simulations. So that's already the first step of our algorithm. So we have a really big circuit of a lot of random quantum gates. And we run this circuit n times. And so each output after a measurement is an n-bit string. So again, we have, well, this is here, it's wrong because this should be capital N. So we run it n small n times, but then depending on how many qubits we chose, we have the capital N bit strings. So, oh no, that's, sorry. Yeah, we have n bit strings because we run it n times, and it has some sort of distribution. Just classically, in terms of statistics regarded, we have a distribution. And then we want to verify the result. Here it is written from the perspective of a quantum computer. So we want to verify the result, and that's something, another benchmark that is called cross-entropy benchmarking. And this is specifically used to assess the distribution that we got. Because if the calculations were completely wrong, we might expect the distribution to be the normal distribution, or just ones that everything is can be regarded with the same probability. So in other terms, randomness. But here we can approximate the ideal probability distribution and compare it to the one that we have achieved on our computer. The problem with it is it's not a benchmark that is 100%, let's say, verifiable, because since we are not able to calculate with a classical computer that quickly or that well, we are only approximating. So we don't have an answer that the Willow quantum computer actually came up with the correct answer. But we can say that it almost definitely did. And this is what was used here, and classical computers have to do a similar thing here. So it's also presented with a quantum circuit. It needs to simulate it, and then we can check whether it's correct, although in this case it's impossible because it is very hard to calculate. So let me just go back that the choice of the benchmark itself was one of the reasons that people laid it out on the quantum supremacy claim. But it is a benchmark that is probably the most popular one, and that other companies have also started using for proving quantum supremacies of their systems. Now, this is almost in the words or reworded from the article itself. So this is what Google is saying in terms of the challenges or what they want to tackle next. First of all, if we want to achieve much lower error rates, or error rate that would make scalable quantum computing, or in general quantum computing, viable to have some applications that are practical, it would be extremely resource intensive. So again, to achieve a 10 to the minus 6, remember that the floor that they broke through was the 10 to minus 6. So it's already not a fantastic error rate. But to only achieve this, we would need over 1,000 qubits, which no machine has so far. And again, those have to be qubits that can be arranged in an area where the connectivity is fairly strong. So it is a very big task. The second one is that syndrome measurements per cycle, they increase quadratically with the code distance or size, which will introduce additional scaling challenges. So essentially, we're talking about the syndrome measurements, which are not the physical qubits, and they will increase a lot, not even linearly, but this is another thing that as we increase the size of our code, will become much, much more difficult. And the third thing is that, just to sum up, the achieved logical error rate per cycle this is a quote. So it's still many orders of magnitude higher than was expected and precludes larger fault-tolerant circuits. So here, so far I have been talking about the achievements that were made, but here we're seeing a bit of a different side of the coin. So while it is a huge achievement in the realm of quantum error correction, it's not a breakthrough that will suddenly make viable quantum computation viable on a larger scale or in practical implementations. So now it's useful to look what Google is planning next to do. And here they have laid out a roadmap. It's a roadmap for multiple years, as we see 2025 is only milestone 3 or later. So we're only in step 2. And to be honest, the first 2 steps were the most, well, so to say, flashy ones, the ones that showed the most. The next ones might seem insignificant, but we need each of them to be able to have quantum computers that will be viable. So first of all, that was achieved at the Beyond Classical with Sycamore in 2019. That was this achievement. Now, our current achievement that we had is a huge achievement in quantum error correction. So the achieved logical qubit error rate is 2 to the power of minus 2. And next thing that they're going to be working on is building a logical qubit that is long-lived. As I described, the connectivity between the qubits is important. A lot of things can become dysregulated in the logical qubit itself. So to be able to have algorithms that are more complex, they will have a longer runtime. So our logical qubits have to be able to survive through the lifetime that is required. This will be the next thing they will be doing. Next, they will be creating a logical gate. So with the logic qubit, we'll be able to have practical gates. Here we're introducing already some practical computation that can be done. Next, as I said before, with the over 1,000 number qubit, over the 1,000 qubits that we would have to have, this is what they'll be doing next. So just making more qubits that are still as robust as before. And finally, we will have putting all these building blocks together, we'll have a large error-corrected quantum computer. And this would be the greatest milestone of putting, well, potentially getting out of NISQ era quantum computing. Now we can revisit with the knowledge that I hope I was able to convey, the same claims from the beginning. So first of all, the processor is operating below the threshold, which is a really big achievement here, and something that will allow us to have quantum error correction that is better and to not use as many resources as we would have to. So this really unlocks a lot in other branches of quantum computing. Next, the real-time error correction, which is also a big achievement. In this case, it's an achievement in the realm of classical computing with the decoders that we talked about. So the neural network one and the minimum weight perfect matching. Next we have the achievement, the beyond break-even achievement, where the arrays of qubits have longer lifetimes than the individual physical qubits do. Well, we didn't talk that much about it, but the paper does prove that that is what happened. And finally, the claim with performing a computation under 5 minutes compared to time that is over the lifetime of the universe. This I am personally slightly skeptical about, since it's not very clear cut of how much of an how much we can expect from this claim, because there are different algorithms and stuff and such, but it definitely proves some viability, and definitely proves improvement. So even if we do not believe it is the proof of quantum supremacy, it definitely is proof if compared to the Sycamore processor. Here are some of the references. The first one is the Nature article, the second is the blog post. And the last one, if someone wants to go deeper into surface codes, this is a very good interactive introduction to them. And that's the end of my talk. Are there any questions or comments?
Thank you. Thank you very much, Alex. That was a great presentation. There is a question from Mohammad Reza. In the slide for the next step, specifically for logical gates, why 10,000 physical qubits? I assume it's because of 2-qubit gates, but still achieving that sort of correlation would demand that many number.
We need a lot. If you compare, for example, something that probably the most popular algorithm, so Shor's algorithm that might be able to break RSA encryption. So this is something that people are often asking. Well, you have your quantum computers. Are you breaking RSA or not? So to be able to approach this, for example, right now, there was another breakthrough actually in this department, but let's say 1.5 years ago, we were able to use Shor's algorithm for the number 21. And we need orders and orders of magnitude more for it to be able to compete with RSA. So not only do we need more qubits, simply to be able to correct errors and simply to be able to have viable logical qubits and machines that run correctly. Well, we also need more qubits to be able to perform any algorithms that are actually important. Important as in practical or viable, not only from quantum computing perspective, but more overall scientific perspective.
Okay.
So yeah, I hope this answered your questions. And then any more comment on quantum neural networks and their supremacy over classical neural networks? This is more Pavel's domain, I'd say, not mine. So maybe I'll,
Okay.
if you could answer
Yeah,
this one.
but the question is directed in reference to this chip by Google that you are discussing.
Yeah.
So do you have any slide in regard describing quantum neural networks or possible scheme of that?
Here, the neural networks, as far as I know, are classical. Those are classical real-time decoders that they're using.
I see.
Since the decoding that we're doing is, if I go to the previous slides.
Yeah. There was one slide. Yeah, something.
Yeah, essentially this. So we have this, and we need to be able to decode it. So the reason they're using real-time classical decoders is because they're fairly reliable and fairly optimized. I think there is potential in using quantum neural networks, for example, or other quantum methods to be able to, so to say, catch up with the quantum computer, but this is the one that worked for them.
Yeah, how about the next slide? On the next slide, there was a slide with this matrix of interconnected qubits.
Matrix.
Yeah, this one. I mean, this kind of matrix.
Yes.
So, yes. So the question is in regards to the system which is given here. Can we think about functionalization of the system which is described in terms of quantum neural networks? So how if you imagine that you have 3 inputs at the very bottom, let's say, and 3 outputs on the top, can you think about possible quantum neural networks in that regard?
Pavel, would you have a comment here?
I'm not sure. So I'm not sure if I remember. So Krzysztof, could you
Yeah,
maybe
so
please
we
repeat?
have, well, so this is like array of interconnected qubits, right?
Yes.
Like
Yes.
transport qubits most likely, right?
Mm-hmm.
So if we introduce three inputs at the very bottom, let's say we functionalize the inputs as we associate the bottom line as inputs and the top line as outputs. Can we think about the system of interconnected qubits as a sort of quantum neural network? And was this attempt already tried?
So
Yeah, that
yes, yes. So in some sense, yes. So actually, so yes and no, because there are also different approaches to quantum neural networks. I think that the most popular is rather based on let's say quantum gates considered as or parameterized quantum gates considered as let's say our quantum neurons. But in this case, I'm not sure actually.
I
I
mean,
think
it's just open question or
yes.
just open remark, right?
Yeah. I think I'm not aware of the approach that you described.
Well, it's just a kind of idea which comes during
Yeah.
listening, right? I mean, nothing more, right?
But anyway, yeah, it could be interesting. We can
Or,
try to look for some articles. Maybe there are some such approaches, but
okay, I see, I see. Okay, thank you.
okay, thanks.
Thank you for the question.
All right. There's a comment from Mohammad Reza, right? For sure, algorithm. I had heard of much high statistics, and it only makes sense. I was thinking in terms of single gates, which was bizarre. Okay, so it was just a follow-up comment to your answer, Alex. Yeah. So actually, I'm still thinking about these connected qubits, let's say, right? Because I'm just wondering how exactly the information could be processed here, right? Because when we have quantum gates, then it's natural, right? So we have the qubits, we have quantum gates, and these quantum gates could be parameterized and they could be tuned. So this could be some kind of training of this, let's say, quantum neural networks. But here, when we just have connected qubits, so I believe that we would need to have some quantum gates, right? But yeah, because otherwise I'm not sure how exactly we would need to perform the computations in such a model. But maybe there is such a
The problem is that first of all, linearity principle, which governs the quantum mechanics, right? But I mean, it's like if you have a system of n bodies interacting such a system, so Schrödinger equation for n particle system is pretty much linear. It's linear actually. It's diffusion equation in imaginary time. It's pretty much like that. But the problem is that when you start to think on the qubits in separated way, so you start to consider, let's say, wave function of a single qubit, then you end up quite much in integral differential equations, which are nonlinear. So for once, it depends on the perspective. If you treat three qubits as a kind of independent at the very beginning, perhaps the system can have nonlinearity, and this nonlinearity that propagates via layers constitutes the neural network. But otherwise, yeah. I mean, it's just a question of some, let's say, I mean, basically, n-body interaction can be seen as non-unitarian evolution in terms of single body wave function, something like that.
So in some sense, in such a model, the computations could be conducted thanks to the interactions between qubits, right?
Yeah. But
Mm-hmm.
very open issue is at very because actually you can try to pump 3 qubits which are separately at the input,
Mm-hmm.
and but at the output you have n-body wave function, so you have to somehow separate this n-body wave function into 3 entities. Then
Mm-hmm.
you can interpret each entity as a body, as output 1, output 2, output 3. That's a little bit kind of troublesome, but
Yeah.
somehow I see no boundaries in such functionalization of the structure as shown here.
Yeah. And another question is, can we somehow control computations in such a model, right? Because when you have classical neural networks or the typical quantum neural networks, we know how to perform training when we have data. And in this case, the question is how the computations could be controlled, or what exactly could be tuned when we train a model on some data, right? Are there any parameters?
Interconnectivity
Mm-hmm.
interconnectivity
Qubits. Mm-hmm.
between qubits. But
Yes.
basically, this interconnectivity between qubits is most likely predefined by external magnetic field source, most
Mm-hmm.
likely,
Mm-hmm.
plus some possibilities of external static electromagnetic field. But let's say in first attempts to quantum neural networks, there was a random guess method for
Mm-hmm.
getting values of weights. I see no obstacle in trying to have a random biasing
Mm-hmm.
electric and magnetic field, of course, in a certain reasonable scale. So certain functionalization is searched, but probably this could be more. I mean, technically speaking, this is a problem of quantum transport, which emerged
Mm-hmm.
here. So
Okay.
you try to transport the information from very bottom to very top. So that's
Mm-hmm.
so basically that's supposed to be done in a formalism of an interacting quantum bodies. That's pretty much, and this is most likely due to that there will be in transmon qubit formal transmon qubits Hamiltonian for yeah.
Mm-hmm. Yeah, interesting. So if yeah, Krzysztof, if you have some papers about it or some other ideas, feel free to share, and we can maybe brainstorm more.
There
Uh,
is a coming conference on that, right? A workshop.
yes, on quantum machine. Yes. So are you going to talk about it as well, or?
Yeah, I wish to have it would be great to have a chance to do it, right? Let's say in that way. But yeah, so it's up to you to make it happen.
But would it be included in the talk that you submitted? Because we are already included your talk in the agenda, right?
Well,
So.
so I will include this. I will include this issue. I will conduct certain type of discussion in that way, in that direction during my talk.
Mm-hmm. Okay, good. Thanks. Yeah, there might be some interesting discussions. All right. Do we have more questions to Alex or some comments? No more questions. Okay, so Alex, thanks once again. Before we finish, I will share my last slides for today,
Thank you
just
very much.
to yes, just
I
to
hope
invite
people present
everyone.
were able to learn something new about it or
Yeah, definitely,
understand
definitely.
something of how the processor works.
Yes, definitely. I think that was very, very interesting discussion as well. So thanks for that. Just a few last announcements at the end. If you would like to stay connected, feel free to join our groups, mailing lists, follow our profiles, and so on. Join our Discord server as well. We would like to thank our strategic partners once again for supporting us: Sonovera R&D, Cogit, Quantum.io, Onyx, and FinQubit. And we would like to thank our honorary partners for helping us advertise the event as well. You can also donate our activities. So all the events that we organize are free for participants. So this is one of the actions that we have. But you can donate us if you would like, and especially if you are in Poland, you can donate 1.5% of your tax as well. And we would like to invite you to attend our next episode, episode 66, and it will be an on-site meeting in Warsaw on April 14. So during the World Quantum Day. I probably will start at the same time at 18, and if you join our mailing list or join or follow our profiles, you will see the announcements within the next 2-3 weeks. Or probably closer to the beginning of April. And as Christoph said, there's an upcoming workshop on quantum machine learning. So it's actually the 5th edition of our quantum machine learning conference, which will be online. I know that if some of you have already signed up, so we'll start sending invitations soon. It will be on March 15th. All right, that's the end, and maybe I'll just leave these links here for the last time. I see there are some new comments. No, there are just some things, and oh, there was a nice link from Crystal that Cody gave a talk about Willow, which is on YouTube. Thanks for the link. I will just copy it and share it with our community on Discord. Thank you for that. Good. Yeah, I will now stop sharing my slides, and I will also stop recording.